Okay, this is lecture 13 of our Design Technology Co-optimization course. Um, lecture 13. So the last few lectures were devoted to the understanding of selective epitaxial growth, and now let's come back to the FinFET fabrication process. Uh, Here you can see the final structure we have considered up to now, and this vertical line is corresponding. Actually, there are three vertical lines, and they are corresponding to the dummy gate, and these horizontal lines are corresponding to fins. And what we have done up to now is spacer formation. You can see that here, and also here. There are spacers, and between these spacers, we have just exposed uh, silicon fins. So yes, these are silicon fins. Later, on top of these silicon fins, we will try to um, attach metal to have a ohmic contact. However, uh, right now these fins are quite small in its volume, so it is quite a small one, so it does not provide us a sufficient amount of conductance. Simply speaking, source and drain uh, resistances are too high, so we wanted to increase the conductance by applying selective epitaxial growth. So if we make the cross-sectional view of this system in simplified version, then it just looks like this. Mm, what is this 20 nanometer gap between these two fins? Yes, in this case, this is corresponding to 20 nanometer in our case. So here we have one fin and another fin that is corresponding to one fin and another fin. And of course, in this vertical direction, we will have the spacer and another spacer that terminating this fin, but that is not considered. We will just perform, first of all, two-dimensional simulation for this epitaxial growth. The reason why I'm considering this 20 nanometer gap, the realistic one for our 7 nanometer FinFET technology, is actually it is important to make a certain distance between these two fins. Okay, so anyway, now this is 32 nanometer, and this is 7 nanometer, and we have a 20 nanometer uh, distance between these two fins. So let's just try to perform a kinetic lattice Monte Carlo simulation for this structure. So if we introduce the thickness of 4.5 nanometer, then how does it look like? It is the cross-sectional view of this system. So we can easily say that these two fins are still separated. Here we have one fin and another fin, and since we have a 20 nanometer spacing, so 4.5 nanometer of growth doesn't uh, along the side or direction doesn't introduce merged fins. And when we have a look at um, here, you can see a certain surface, and also we can see on other surface and on other surface, and also we have something here. And please note that this is corresponding to 111 surface, and also that is corresponding to 111 surface. And what is this? This is not corresponding to no, not corresponding to 100. So this is corresponding to 110 surface. Uh, this top surface, this one is corresponding to 1001, but that is now disappearing because here we have a quite slow 111 surface. Mm, this is quite well discussed in our previous lectures, and this is corresponding to 311, but that is more or less intermediate, and they will be catched up by this eventually this 111 surface. So this is the structure after a short period of our epithelial growth is done. The next one is what happens if we keep this procedure further and further. So let me just double the number of atoms. So if we add more atoms, then maybe you can say that, okay, if this is 4.5 nanometer, and if we just double the atomic number of atoms, then maybe this is 4.5, and also another 4.5, so 9, and also 9. Still we have 2 nanometer, but you can see that actually here we have a very steep decrease of its volume. So when we double the number of atoms, actually they are just rigid. So here and there, we can see that these are rigid. It looks like mushrooms. Still we have here and there, still we have 110 surfaces, and in many cases here we can see also 111 surface, and almost this one, so lower angle surfaces are eliminated. So it looks like just a merged fin. So do you like it or not? So if we consider the resistance of this source or drain, then it is quite much beneficial because here now we have a sufficient amount of additional volume to reduce the resistance. But problem is if this is N MOSFET and if this is a P MOSFET, then this is not a good sign and we must avoid it. Also, problem is can we just control whether they are merged or not merged? The shape, if we cannot control the shape, then it will introduce the fluctuation or variation of source and drain resistances. So usually we don't like it. I will just show you the result. Just stop before merged or bridged fins, but depending on company or situation, we can find different cross sections. So please consider my simulation result as just one of a possible profile or shape. And also, there is another thing we have to consider. Can we trust this result? So my question is here, if we keep this kind of simulation or yes, KLMC simulation further and further, then of course we will have a slow growth of this one-on-one surfaces, and eventually it will go to this way. So volume is slowly increasing. Yes, we know it. But point is, now here we have something. Even in this case, the growth rate will be given by, yes, something like this. We have a faster growth and slow growth and slow growth. And this growth rate along this negative uh, direction will be the same with this positive direction. But it means that we are omitting a very important factor in this selective epitaxial growth. That is, we need to something to provide silicon. So maybe you remember DCS is required to provide silicon atoms. However, now you can see that this here we have a gas phase, and now we have a bridge, and in this part, how can we supply this DCS gas into it? So that is not possible. So it means that we do not consider the motion of gases and some certain materials, and also its ventilation, their ventilation is not considered. We just assume that gas is uniformly distributed. So in this case, I think that it's okay because the spaces are just open to the top, so gas can be easily ventilated. However, in this case, once the window is closed, then there is no way to provide certain materials to keep this growth uh, procedure. So please do not overtrust our result. This is just showing certain trend. So as I told you before, in practice, companies just shows some companies shows separated and some companies shows merged between for N MOSFET and P MOSFET. Of course, they should be separated, and we have a uh, certain fin hole width or fin pitch to separate the NMOS island and PMOS island. But right now, I will just stop here. So without further trying to expanding our fins and having the eventually merged one. So I will just stop here. That is one thing I wanted to say. But please note that this is not the only available option. There can be another option. Uh, and if we stop somewhere between, then we can find a condition of unmerged fins. And yes, here we have some notation or statement. The fin shape can be well approximated. It means that starting from this fin, the final fin shape quite uh, well approximated by certain simple geometric rule. So starting from here, for example, let's say this is just half of our fin thickness. So where are we now? So we are now talking about the position, for example, corresponding to this one. This one is corresponding to this one. And if we proceed half of fin thickness, then we will have the starting point of our fin shape. So we will have, of course, here. In practice, we have a small difference here. Of course, a small difference here. Although we prevent or we suppress the growth attached to the silicon dioxide, but still we have a very slow, although slow, but we have a growth along this direction. But that is neglected. So small error comes here. Once after we understand this error, then the slope. This slope is actually really well given from our structure. So this is given, and now we can see the distance. So what is the maximum distance for our this length scale? Of course, here we have the spacing between fins, in our case 20 nanometer. So at most we are allowed to have just half of it. For example, this length should be shorter than 10 nanometer in our example. And once we have this position, so corresponding to this position, then, oh, sorry about that, this is not 100 surface, so that is my mistake. So we have a 110 surface. Now we have this vertical line, and after that, now we have to come back. So here we have another the same slope, and it will be kept till the end of our fin center. So this is corresponding to this one. Of course, you may say that, okay, this part is a little bit rounded. Yes, that's true. But, well, if we spend a little more time and expand it further, then eventually they will be sharper. So you can see that this is the shape of approximated or geometrically calculated shape of our source drain region. So beyond this level, increasing it further, that is not that easy, because this is once we arrive the maximum level, then there is no further expansion to the lateral direction, and only top is affected by this consideration. Okay. So anyway, this is the way of our modeling. Okay, so now let me before moving to another structure. So let me just show you the impact of a fin height. We started from 32 nanometer tall fin height, 32, but in many cases, fin does not start from its full length. I will talk about this topic later in today's lecture. But anyway, for a while, just to assume that our fin height is not as high as its full height. Instead, say that this is just 8 nanometer. So you can see here 8 nanometer. If we start from this relatively short one, then what will happen? In this case, okay, vertical growth and lateral expansion. So you can see that now we have more uh, expansion here and there. Although we keep the same amount of same number of atoms, but the profile looks completely different. So same number of atoms in the used in last slide or was considered, but its profile is so much different. So details are important in our simulation. So please be careful. Well, anyway, now let's come back to our original Armstrong craft. So using the 1 nanometer, 1 nanometer, 1 nanometer cube as a basic building block. Then in today's homework, you must construct a test structure which is quite similar to our original structure. So please have a look at this one. And this is actually corresponding to a part of our structure. So simply speaking, you are now looking at some point nearby here. Although we have three fins, in order to our life as simple as possible, I just took two fins, so you can easily understand. And yes, here we have two fins. This is a fin, and this is another fin, and their separation is of course 20 nanometer, and fin width is 7 nanometer. So in this case, also here we have a 7 nanometer fin, yes, this guy, and separation 20 and 7, and once again, and in order to consider another fins surrounding these two fins, we have another 20 and 20. That is corresponding to another 20 and another 20 in this direction. You understand, this one just shows a part of our wafer. And another one, this is the y-directional constellation. And here we have a horizontal one, x-directional one. And here we have a 34 nanometer corresponding to 9 for what? 9 for our spacers, and also 9 for our spacers. And in this case, we have a 16. This 16 nanometer is reserved for our source drain region. So please note that colors of the regions are slightly changed from our original, the latter simulation or emulation result, but please neglect it. And now we are ready to test the selective epitaxial growth. So in your exercise, please set this model in this way. Of course, region name uh, itself can be changed. So I call it this red one as a fin, and the later one which will be grown from this fin is named as a source drain, but you can name them as you want. So the point is we need to add this one. For example, here originally we have a fin, and if we do not include this source and drain, then it is expected that one layer of our added source drain will be added. After that, it tried to add another layer, but it cannot find fin. It just find the source and drain. So it is not selected in this model specification. So even though you ask to grow very thick source drain layer, but you will find only one layer of a source and drain. So therefore, you need to include this source drain itself should be included. Maybe you can ask me, why don't you just include the growing material itself in this model specification automatically? But sometimes it is not. So that's the reason why I just make freedom to select or unselect this region. Okay, so then first try our previous isotropic deposition command. So you can see that now you can do it quite well, depo and iso and something. So if we perform our deposition in an isotropic way and say a given thickness of 9 nanometer, then you will have this form. This is just a cross section. Of course, this is a three-dimensional structure, but we just make a projection, so you can have this cross section. And with the same scale, I just show here KLMC result, and this is our process emulation result. And you can easily understand the shape of this lead fin is the same. However, the green one, the source drain, selective epitaxial growth, shows much difference. Why do we have this difference? So there are. So let me just describe the difference. One meaningful difference is here we have this sloped 111 surface nearby the bottom. So for example, starting from somewhere here, we have certain angle, and also we have a certain angle here, but that is missing. So here we have a silicon dioxide corresponding to the STI. So we must suppress growth along this direction, but that cannot be considered in our implementation of an isotropic deposition because it doesn't care about its neighbors. And another one is here you can see certain angle. Yes, but you can also understand this angle is slightly steeper than this one. This one is of course 45 degrees because we are now just considering the cubes. So the best one we can have is just 45. But this one is steeper, about higher than 50 degree, 53, 54, I don't remember exactly, but this is steeper. So this is one thing. And okay, then if we say this is steeper, then are we happy enough? No. Here you can see that there is, even though we accepted this 45 degree, but we can also find that there is a severe growth along this direction, also this direction. But in this case, our growth along this direction is really suppressed. However, we have quite a fast growth along this direction. So, shortly speaking, our current implementation of isotropic deposition is not that much suitable to mimic the KLMC result? Well, I told you that from the beginning of our lecture course in this semester, our capability for source-drain epitaxy is limited, so we have to understand the inaccuracy in our generated structure. Yes, that's true, but I think this is too much. So, mm, so during the break, uh, in 1 week ago, I made a new statement in our Armstrong craft that is named as growth instead of deposition. So in this new statement, we take three spec arguments. One is reason, okay, so we will grow source and drain, yes. And another one is material selectivity. Yes, so we had this capability previously. So it is not changed from deposition, and we have no command corresponding to, or no input argument corresponding to mask that is not implemented in this course statement. Instead, we have a little bit different specification. So that is the number of boxes to be added. So since we cannot precisely predict the number of boxes, so this one is just used as a criterion for selecting the final structure. Minimum number of boxes which will be added. So if we say this way, it means that at least we have to add 12,000 boxes into our system. So if we have a larger system, then of course this number should be increased. And if we have a lower system, then or smaller system, then of course this number should be lowered. Okay. What else? Mm, yes. Another one is another caution is please do not increase this number parameter too aggressively. If this number is too large, too high, then this loop cannot be stopped. So because once after this source and drain region is sufficiently grown that it cannot find any further place to add additional boxes, then it just try and fail, try and fail, try, fail, because in its implementation, we just use do while statement in my C++ implementation, and this while condition is the actual number of added voxel is exceeding this number specification. So please do not increase the number parameter too aggressively. Always try to increase um, continuously or with caution. And what's the difference between this growth statement and previous depot statement? And in this case, we check the existing surfaces. So that is the difference. For example, along 001 direction or the growth of 001 surface, it considered this way. Okay, previously when we had just the isotropic depot, then if this is the front of our material, then we just add one more voxel on top of it. Yes, that was previous behavior of our isotropic deposition. But now, in this case, this growth just consider this condition. Okay, is there anyone surrounding this target voxel? Yes. First, it tries to detect whether these four surrounding uh, positions are occupied by valid material. Once we have this condition, then we can say that, okay, there is uh, 001 surface already. Then now I can introduce this new voxel. Otherwise, it does not include or does not add this new voxel. So that is a simple rule we have. Of course, this is just for 001 surface, and we have other surfaces. For other surfaces, we have also different rules. And I'm not saying that this is quite rigorous, but it is just to try to mimic the architectural course. And also another one is, okay, giving up the precise description of a 111 surface. You know, 111 surface have a steeper angle uh, with respect to this xy plane in our coordinate system. So its angle is slightly higher than 50 degree, but we will just start here with 45 degree. So please understand the limitations of my current implementation. Well, then, uh, then now let's have a look at the result. When the number in our example system, so when the number of voxel is set to be 12,000, then we have this profile. So this is once again KLMC result that is exactly same as before, and now we have the improved result. What is the improvement? Now you can see that here we have almost no growth in lower part, and here we have a certain angle. L, this is corresponding to one moment surface. Of course, here we have a steeper angle, but please understand this is the limitation of my implementation right now. And another one is previously we had quite a steep quite a fast growth along this direction, but now that direction is completely, actually completely suppressed. I think that that is in some sense too much, so we have to allow actually a little slow increase along that 111 surface, but to me it was very difficult to implement it that way. So therefore, I just completely suppressed the growth along 111 surface. However, since one moment directional growth is anyhow quite slow, so the final shape of our structure looks much better than previous one. So once again, let's have a look at our previous one using isotropic depot. So although not every detail is well matched, but it's much better than previous one. We will stop here. And now let's go to our real three-dimensional shape. So of course, this result is obtained from our three-dimensional structure, and it's just a cross-section is shown. However, in realistic case, we usually perform so-called cavity etching. What is this cavity etching? So here we have originally fins. Where can you find the fin? Yes, now you can find here fins. And the, the result we have shown up to now is just to add more silicon so surrounding this fin. That was our uh, result up to now. But in reality, what we have done is cavity etching. This fin is intentionally etched away. So this one is intentionally etched away. In this case, I just used 32 nanometer Tor and isotropic etching to completely eliminate this structure. What is the reality? Uh, Actually, so also this information is not that much clear, but many cases the cavity etching can even deeper than this fin. Of course, below it we have unexposed fin, so covered by STI, and according to the literature, even this cavity etching goes deeper than this STI level. Um, so, mm, so this shape is a little bit simplified one. And also, we have made another simplification, the fin underneath spacer. So here you can see, yes, here fin. And since this is protected by our spacer, if we just perform perfectly anisotropic etching, of course, this fin underneath the spacer can be saved from this etching process. But in reality, also we intentionally mix this anisotropic etching, also isotropic etching. So actually, yes, certain amount of silicon fin underneath the spacer is etched away. Uh, but that is not also considered in our simple example. Then you can ask me this question, why do we need cavity etching? So please note that the reason why we do this job is closely related with silicon germanium growth, especially in the case of our P MOSFET. This selective growth of silicon germanium, not pure silicon, is quite important because this silicon germanium layer provides certain compressive stress to our channel. Where can you find the channel? Yes, here you can find the pin, and that is stressed by this silicon germanium. If we introduce this silicon germanium and it push, and also if we have here silicon germanium, it push, so this silicon channel is compressively stressed, and that is quite beneficial to increase mobility of a hole. So that is one of the most important performance booster in state-of-the-art devices. So simply speaking, we have to maximize this volume of silicon germanium. So if we just keep this silicon fin is here, and if we introduce additional silicon germanium just surrounding this existing silicon fin, then that is not that effective to introduce a sufficient amount of compressive stress to silicon channel. So that's the reason why we need to make a cavity etching. So we have to maximize the volume of a silicon channel. So, well, now I understand. Cavity etching is really required, and when we start from this etched profile, things are a little bit different. So please have a look at this one. So growth after cavity etching. Now the structure is no longer uniform along this channel direction. You know, this is the channel direction, and here we have a fin surrounded by spacer and fin also surrounded by spacer. And now you can see that here, starting from this point, now we have a downhill of our grown source drain epitaxial layer. Okay, so it means that the contribution from this side and another side is more dominant than the growth from the bottom. If the, uh, the contribution from the bottom is dominant, then of course, since the bottom is just uniformly distributed, as shown here, so the profile will be uniform. However, since this uh, contribution from side, this side and that side is dominant, therefore now we have a certain variation along channel direction. It is quite much understandable because please think about the distance. From this side, the halfway to go is just 8 nanometer, and from here to there we need just 8 nanometer to arrive at half of it. And how about this fin height? Fin height is 32, so even we wanted to go just half of its height, fin height, we have to go 16 nanometer. So simply speaking, this the space for our source drain epitaxial growth is now very tall and narrow. Tall means that in this direction it is tall, and in this direction it is quite narrow. So the contribution from bottom is not that important, and contribution from this side wall in this case, not side wall in this case, but anyway, from growth from spacer part is quite important. So now we can find that, yes, here we have a certain change in its shape. So is it really true? Yes, actually. This one, this shape really observed in some literature. And point is, if we add more voxels, then eventually now here we have once again 001 surface, and that one is now grown. And after some time later, now it becomes just flat. So, but why do you, why, the reason why I'm showing this intermediate one is in our current implementation, now we have just 20 nanometer, and we are quite close to each other. If we allow further boxes into this epitaxial layer, then eventually they will be just merged. So I just stop here. Uh, but in reality, mm, this 20 nanometer is, well, if we just consider 7 nanometer and 7 nanometer 20, then if you just apply our previous calculation or geometric calculation shown here, if we just follow it, then the maximum, yes, if we just follow this way, then even though when we have a 20 nanometer, the overlap is not that much. So it means that since we have a steeper theta value, so higher theta value, then 45 degree. So the situation is a little bit overemphasized in our Armstrong craft because we have just 45 degree, and in reality we have a steeper one, so we have a more margin to expand it. So during that time also we can have a better profile. But anyway, uh, depending on the process condition, this kind of downhill slope can be really occur. So I think that although this angle is not perfect and we completely suppress the over this fin layer is suppressed, so there is many limitations, but I think that it is much better than our previous isotropic deposition. So uh, now I wanted to conclude today's lecture, where we have spent a few lecture slots to this source and drain epithelial growth. First, we consider the crystal structure and experimental data and KLMC result, and how can we bring it to our Armstrong craft. The final result we have at our hand is not that much. That is fine. It does not provide us an exact angle, and we have many approximations, but I think that that is the best we can do right now. So we will stop here, and now we are ready to continue our FinFET fabrication process. So our homework number 13 is like this. Please uh, uh, play with our simple example we have seen in lecture 13. Then, using our newly implemented growth statement, then please try to grow the epithelial layer. Of course, here you have number specification. So with the different number specification, you can build a smaller epithelial layer and larger epithelial layer. That is your own exercise. Now, please enjoy this one, and of course you can also try to make a merged one or unmerged one, and if you keep this number further, then eventually you will find the beautiful diamond structure. uh, One thing I wanted to say is, if you perform this overcooked uh, emulation, then you will eventually have this kind of a shape. And in this case, this angle is right angle. So that is simply because our angle shown here is 45 degrees. So please understand our original shape. The realistic shape is not this way, slightly steeper and steeper. That is the one we have in reality. But except for this one, we can just enjoy this kind of exercise. So please make a sufficient number of exercise during your homework. Due is next before our next lecture start, and our TA will upload the most up-to-date version quite soon. Right now, I'm not sure we have the updated version. Then please check it later. And I said that the thing you have to do is just this one. So specifying this model specification and perform this one. Then you will have something, and please adjust your numbers to have a more reasonable result. And the final comment is model had previously some body body argument like select. So these materials are select. And here I introduce another one named as neighbor. And this neighbor means that from spacer, our silicon germanium or silicon cannot grow. That is obvious. However, I'm saying that when we have a spacer, it is counted as a valid surrounding plane material. So maybe it is not that easy to understand. So please add this specification. If you don't have it, then actually it works without this neighbor one. But in that case, you will have a slightly distorted shape in this spacer nearby the spacer. Usually spacer is made of silicon nitride, and as we have seen in our previous lectures, silicon nitride is not that strict in this preventing epitaxy growth. So here we have silicon dioxide, and silicon dioxide is very strict in its growth. So on top of silicon dioxide, it is almost impossible to have a nucleation. However, on silicon nitride spacer material, we have a sufficient amount of nucleation. So that's the reason why I made this neighbor statement. But you know, as you can see, this implementation just on and off, whether that is considered as a neighboring material or not. So in reality, this one can be just expressed with many different parameters, but our model is quite much simplified. That is also limitation of a current implementation. Okay, that's the current situation, so please understand. Okay, so let me just conclude today's lecture. Now we are ready to come back to feedback. Today you are just testing our new capability growth statement, and we will apply this growth statement to the entire system in next lecture, lecture 14. Okay, thank you for your attention and see you next Monday.